part 4 and final for circuit number 6, the traffic light controller using CMOS logic ICs, or you can use TTL logic ICs. This circuit is a pedestrian circuit. Normally you would have traffic lights with the pedestrian lights, but there are times when you do not install pedestrian lights, so that's why it is provided as a separate circuit. But where the pedestrian lighting is required, we have this circuit where you can actually construct it and use pedestrian lighting. As you can see here, we have the same timing monostable circuit, our favorite monostable circuit, using the 555 timer. Let me try to zoom it a bit. Okay, right, this is our monostable timer, the classic monostable timer. You can have this one, or you can actually have two of them, which means for the P1 you have a separate timer, and then you separate here, this here, cut out here and connect to the separate timer, which is pin number 3. So pin number 3 is connected to that one, and then the other timer, the pin number 3, is connected to that one, which you separate from there. So you have a separate circuit which is having a separate timing function. For this one, the timing is going to be the same for both sides. So if you have going to have two, it means here you have a separate circuit, meaning here also the input, the one that is going to strobe, is actually going to be different again also. So separate timing that you can modify if you want, but I have used one timing circuit. So you have your green lights, green signal, remember, from the manual control board, the P1 and the P2, they are coming here, connected here, and then you have your output 4 relays to actually operate using this relay driver. But also this driver is used to strobe the timer. So you have 4 driving relays, but also using the strobe, and then timer, and then our NAND gates here, 2 ICs, 4 NAND gates in each IC. So we have actually 2 logic ICs. But before we start to describe what's happening there, we go as usual to our script, electronic waste benefit, the philosophy of using electronic waste material to actually build our circuits as much as possible. I'll be glad to hear from someone who has actually built any circuit 100% from recycled material. We cannot prove it, but it's only self-satisfying. Let's use electronic waste. We can actually do that. And safety, very important. Please make sure you are experienced in working with this, and also prior knowledge is expected. You must know electronics already, or at least have an idea, or you can get someone who know already. Read on the net, there is enough information to learn electronics. Your workshop is a no-go area for children. Please, they are sharp objects there, your tools, they are small objects that they can swallow. They are not allowed in workshops. Please, it's a no children zone. We expect that 10 years and above for you to be able to understand the concepts that we are going to be discussing here. And well, this is not a training for electronics as usual. I've always been saying this. It's a description of how these circuits work. So please have your knowledge of electronics before. And let's use waste. And you can use this traffic light circuit as a training, as a learning aid, or industrial, in schools, in companies, wherever it is applicable. Resources: a computer for drawing schematics, computer for drawing PCB layouts, no programming. This it is a hardware based circuit, so it's not programmable. You need the electronic components, you need the variables, the tools and all that, and the software for drawing, obviously, of course. And most importantly, we need your time, you need your patience, you need your passion, you need your dedication for you to be doing this. And I thank you for your time. I hope you enjoy doing this circuit. And as a final video clip that I'm going to do, whether it's going to be split into 2 or many other, but it's part 4 of the traffic light circuit number 6 using logic ICs. So I hope you enjoy. Thank you. Let's go to our circuit and describe how the circuit would actually work, and then I'll also show you the simulation of that circuit, how it's going to be working. So what we have here is a green signal coming, the P1 and the P2. So any one of these should be green, because you can't have 2 greens at any intersection. So one is green, the other one is not green. So it is like a logic flip-flop, where this is you can say P1 and P1 bar actually. So this one is complementary. One is on, the other is off. So suppose P1 comes on, is a high, meaning this one is a low. So this is high, this high comes, goes there, goes through the diode to trigger that timer. So it means we have a high here coming there and trigger that one, so the output here becomes high. So number 3 is high now. Wherever there is number 3 is high, so this part is high, that input is high. So here also it's a high, because green is high, that part is high and that part is high. So you have a high here, and here you also have a high here. So here is a high, meaning this is a low. So the red signal is a low. So how do we see the green now? The green here is an oscillator. This is just an oscillator using a NAND gate. So you have a high here. If you have a high here, it means the oscillator is enabled, it's clocking, so it's running. So this oscillator starts to run as you have a green, which is high here. So the oscillator is running, and now this one is a high also. And remember, our timer has gone high because of the trigger that is coming through here, because through the diode here comes there and then triggers this one, and then it has gone high. So you have a high and a high there. So this one is a low. So if this one is a low, it means here you have a high. So the green light is on. Green number 1 is on. So what is the condition of the side number 2? Side number 2, because this one is a low. So here is a low, it doesn't go there. Here this low comes here. We have a low there. Here is a low. So this one is a high. So the red number 2 is a high here there. So what is the condition of the green? Here you have a low. So you have a low here. So the oscillator is disabled. Here is another oscillator. Here is another oscillator. So oscillator here, oscillator here. So here is a low. As long as you have a low to the NAND gate, this is a high. You have a high here, we don't know. It depends on this condition now. So the oscillator, we only know that the oscillator is actually disabled, it's not running. And then this low here is also coming here. Here we have a low. It means any low here, we don't care about the other one. So low here, you have a high here. And remember, this is a high, and also this oscillator output is a high. So you have a high here and a high here. Here is a low. A high and a high on the NAND gate, the output is a low. here you have a low, a high output, you have a low output, so it is red here and is off. Here remember it has changed because this one was actually going to green. It was not green. This one was not green. There's no green here. This is low. This was not green, but it's now green, so it was changing from a low, which was red here, to a high. So a high here becomes a low, and here we figured out that the green is actually now a high. So this is green, this is red. So what's happening? This stays on for some time because we have a green here, but we have made our timer here, our monostable timer here, to be shorter than the green period, because this circuit is controlled by the green signal. The pedestrian light controller is controlled by the green signal, because you would want the people to cross when one side is green, which is the transverse side, the opposite side, which is green, and then people will actually use the other road to cross. I think we are all familiar with the traffic lights, these intersections. So this time we'll actually go high, and here we have a high, high is a low here, a low here is a high here. But this will actually go low after some time, some seconds. When this one goes low, it means you have a low there, and if this one is a low, it means this one is now a high. When this one is a high, so it depends on this one now. But remember, this oscillator is running, and that one is off. So this one is running on, off, on, off. It means when you have a high here, you have enabled the oscillator to actually have an output. So this output starts to flicker on, off, on, off, on, off. This one is still a high, so you have a low. This is off. So here is coming on, coming off, coming on, coming off, depending on this frequency of that one. So the frequency of that one determines the on and the off of the pedestrian. So it means it has gone green, people are crossing, and then it starts to flash. This is the flashing. So it flashes. When it's flashing, it's actually warning the pedestrian that please quickly cross, it's about to get red. We are just about to get stopped. It means quick, go off the road. Actually, you can make this time long enough to a point where this one is almost to changing. If it's about to be changing to amber, it means this one is already gone low, and it has actually been flashing quickly. And then if this one goes off, it means this one is gone low, this one is still low, because it's not going to change anything here, still red here and off here. So this one is gone to amber, it goes to low here. When it goes to low, it means here comes a high, this one goes red. But what happens to this one? This one we know it is already gone low, so this one is a high. But if this one is a high, it depends on this one now, remember. And this one is a low, it's gone low as well. This one is a high, so this one depends on that one. So you have a high here, depends on that one. But we know this one is a low. Any low on the NAND gate, this one becomes a high. The oscillator is now disabled. This one becomes a high, permanent. So you have a high and a high here. This one becomes a low. So you have a off. The green is now off. Now the red is on. So this is how it happens. And this circuit here is actually equivalent to that one. So this one and that one is the same. It's only controlled by one timer here, of which you can actually put another timer which is different from that one for that circuit. So you just have two circuits which are actually identical, but they are actually run from a single timer. If you want a different timer, you can put a different timer circuit here. The implication of having one single timer is it means the time for flashing is actually the same for both sides, of which normally is not the case usually. the time for flashing is different, because sometimes the green time here is different from each side, so you need another circuit here. So here, as you can see, the diodes here is just an OR gate. Definitely, if you are going to use one timer, use this setup here, or you can use it in OR gate if you want. If you have ICs that you would want to put around. So this is how it works, and let me show you a simulation of this circuit, but it's a bit different from this one, but plus minus you will see it's almost similar. So here is a simulation circuit. Remember, that circuit is only to pause, to change here those two diodes, remember, into a relay driver, and then here also the green inputs are here, green 1 and green 2. This here, which is in the dotted line, is just a circuit to pause to simulate the green signal going into the pedestrian circuit, and you see it is exactly the same circuit like the particle circuit, only that here we are not having driver, we are having simulation lights, the center light being off, white to ground, because you need only two lights, the green and the red. So but everything else the same. The timing, the t seconds, you can actually change. You change this time here, changes the time it takes to actually start to flash. This timer is only there to actually time the length of flashing time. So let's simulate. It takes some seconds. I think now the computer is a bit loaded. I don't know why it's taking time to actually start to. So you see now, as I was saying, the stepping here, let me zoom a bit. The stepping here is gone to 2, because when you power it on, this one comes on high, it goes off, and it steps this one. But that doesn't matter, we'll change that by stepping anyway. So if I change, because now I'm actually simulating a green signal coming and then going, and then comes here on 2 and then goes away, and then circulate like that. Right, so I go, you see this one goes green for some time, remains solid green until some seconds, which is determined by that one, starts to flash. Now it starts to flash after some seconds. On, off. It's slow. I think the computer is playing around here, right? But you can change around. The flashing time is the oscillator time. This oscillator here, this IC 3A. You change this capacitor so that you change the oscillation time, on off, the on off. Now, so it is flashing. It will flash until I change the green. If I change the green light, it will go straight to red, which means it's going to amber and then red, and then changes to the other side like that. Changes to the other side now, and then allow the green people to start moving on that side. So this is green. Now time lapse, start to flash. Quick, it's just telling people, quick, can you cross quickly, because I'm about to go to red, like that. Then it goes to red, it goes to amber, red, and then green. The other side changes again, comes back, and then wait for some time, and then starts to flash. Quick, can you go quickly, flashes for some time. Well, you can adjust the timing to suit the application, from amber and red, and then green the other side, like that. So you can adjust the timing. Remember, timing is normally adjusted using changing this capacitor here, and also the flash time you can change this capacitor. That's plus minus the pedestrian circuit. And this is the simulation for it. It works. The only difference is the practical circuit is having now relay drivers and the green inputs which are coming from the manual control board, remember. And also you can change around here, and you have different times because the sides are not always having the same time. And now that's your homework, because I think you have learned enough to actually be able to actually put another timing circuit here. Yeah, that's more about it. So as a last part of the circuit, well, I don't know, I think my next videos will be maybe on adapted circuits that have been done by other people that I have reconfigured myself, which I would actually maybe make reference to existing circuits that I have configured to suit what I need myself, and I think it's also good that I share with you. And yeah, I thank you, and for feedback and other questions, if you have questions, remember chauramirime@gmail.com. As always, I thank you very much. I hope you enjoy building this circuit. Yeah, it was a long circuit, but it was necessary circuit, because this circuit will teach you very well digital electronics. Well, unfortunately I don't have analog designs. I have them as modified circuits, the sine wave inverter that I've modified from another circuit that I found on the net. And yeah, and then there are other things that I've done, so small circuits and that, but this I found that they are necessary, they are usable circuits, you can actually use them. I've done these circuits, most of them. The only circuit that I have not built, I can show you from the folders here. I don't know now why it is taking time to open the circuits. Something is going fishy here. Okay, I think it's overloaded now. Yeah, right. Now this is the circuit. The only circuit I have not built myself is the security door system. This one I have not built, but the other ones I have done. I have prototypes. On this one I have prototype on lights controller and peak version. I have a not really a prototype, but controller I've done on this one, the gate controller. The alarm I've done it. The locking system I've done it very long time, I think it was 2002. So I am sure you will enjoy. Thank you very much for your time, your patience, and yeah, I'm sorry, I must actually say on the I think it was circuit number 2, yeah, the video did not come out very well, and much of my videos, well, the sound is not very good. I apologize for that. Yeah, so anyway, we hope to improve later, but I hope it's intelligible, you can hear what I was trying to say. Thank you very much. Give me your feedback, positive, negative, improvements, and anything, questions, comments, and all that. I thank you. Good day, good life.